right, hi Andy, thanks for that introduction. Just a quick question, can everyone see my mouse here if I'm going to be using that to kind of point out things?
Yep, looks good.
Okay, awesome. Yeah, so as Andy mentioned, my PhD focused mainly on looking at background seismic noise that resulted from Earth surface processes such as ocean waves or rivers, and having this middle picture, I'm showing that noise source. This is actually Surfer Dan surfing on Lake Superior in the winter. You can see his ice beard here. But kind of as I was going through my PhD, I don't think I fully appreciated that seismometers record many noise signals that aren't related at all to ground motion. And one of those is the self-noise of the instruments themselves. This is usually how we test them, by co-locating 3 instruments together in a quiet place. And that almost bit me on my last paper in my PhD, so I'll show that example. And then there's various other external non-seismic noise sources that seismometers are sensitive to, and I'll go over those. So I kind of am using this webinar as an opportunity for myself to review all these noise sources, and hopefully it's useful for people out there in the community as well, because I know I surely didn't think about all of them as a graduate student. And so, some of these things I'm just learning myself, and if I'm, make mistakes here, I'm happy to have a dialogue at the end of the webinar discussing these. So here's kind of the roadmap of where we're going. Between the introduction and conclusions, I'm first going to talk about instrument self-noise. How can it impact seismic observations, and how is it calculated? Here on the right, I have a figure of us doing self-noise tests on the Fairfield nodal 3C sensors, which are being used a lot by researchers lately. I'm going to talk about non-seismic sources of noise. These will include temperature, magnetic fields, and pressure. And over here we have Bob Hutt attempting to thermally isolate the top of a borehole casing. Kind of at 2.5 here, I put sensor tilt because it actually is a seismic signal. It's caused by ground deformation, but it's not propagating as an elastic wave like we think of most seismic waves. So I'll talk a little bit about sensor tilt here and some of the applications that you can use with sensor tilt. And then finally, I'll talk about briefly some seismic background noise sources. I'm really going to highlight one study where we're looking at the Great Lakes here, and I'll give kind of a brief overview of what types of surface processes can cause observable seismic signals. And here's a picture of a lovely wife and dog next to a river, and there's been a lot of research lately about trying to use river signals to infer characteristics of the river, such as bedload transport and discharge. And then finally, I'll finish with some conclusions. Okay, so here's a brief overview of Albuquerque Seismological Laboratory. The facility was actually founded in 1961 as a very seismically quiet place to perform instrument testing. We have 2 vaults back here, which are in Precambrian granite. We have 21 boreholes and post holes. Before I came to ASL, I'd actually never seen a borehole sensor, so here's a picture of one. So a borehole is kind of similar to a water well or something. This particular borehole goes down about 350 feet. This is called the Russian borehole. It has a diameter here of about 13 inches. It's one of our larger boreholes. And we're putting in a T120 here to test it down deep. And the reason why we put sensors in boreholes, as I'll kind of show in this talk, is by putting a sensor down at depth, you start to get away from thermal variations and some of the pressure variations that are noise sources at the surface. So this is Adam Ringler, and he's installing a sensor down here in our Russian borehole. We also have a variety of translational rotational shake tables to test instruments. We have a machine shop. We house an instrument depot to support a variety of regional networks. And in total, ASL has about 35 full-time employees. So here's a map of stations operated by ASL. We operate the IU component of the Global Seismographic Network, which are these blue triangles. And really our goal is to have a very large global distribution of instruments and have these be some of the highest quality instruments in the world. Right now, just using the Global Seismic Network, you can record detect a magnitude 5 earthquake or so when you are on the planet. We also run the ANSS, which is kind of a monitoring network for the United States. Right now, I think we can detect magnitude 3 anywhere in the United States. And then we also run a few regional networks. What I don't have on here is we recently acquired the N4 network, which was part of the TA array, which is kind of central and eastern US. And then we also operate portable deployments, such as right now we have about a dozen stations in Oklahoma to record the induced seismicity happening in that region. So what do Adam and I work on? We are part of the instrument testing group at ASL. We define performance metrics for seismic instrumentation purchased by the USGS. We test and evaluate seismic instrumentation. Here again are the Fairfield nodal sensors, and this is an example of our horizontal shake table. So we're trying to drive the response of this instrument here. We develop new calibration and installation techniques. Here's a post-hole sensor, which perhaps would have lower noise than a volt sensor in some of our ANS field deployments. And here, this is showing a calibration technique to get the absolute sensitivity of seismic instruments. So here's a quick review of how we get ground motion. So we have an earthquake that generates some ground displacement or velocity or acceleration. Most broadband seismometers are sensitive to velocity, so it outputs a voltage proportional to the velocity input into the sensor. And then that voltage is recorded on a digitizer, which converts the voltage into digital counts. And we as seismologists, what we get out of the digitizer, our raw data is digital counts, and we want to go back to ground velocity. So we need to do a few conversion steps to get back to what we fundamentally want. One perhaps complication is that the response of the seismometer depends on the frequency of the ground motion. So what I'm showing here is on the y-axis is the relative response of the instrument. On the x-axis, I'm showing frequency in hertz. And this area, the seismometer is considered flat to ground displacement, or flat to ground velocity in this picture. And what that's showing is that if you have a, let's say, 2 centimeter per second signal, or which would be huge, 2 nanometer per second signal here and here occurring at different frequencies, it's going to be recorded the same on the instrument. But there's something called a corner frequency here, where at longer periods, the instrument becomes less sensitive. And a lot of seismologists I've talked to, and I kind of thought this myself, refer to this kind of area between these 2 corners of the instrument as the passband of the instrument, and that perhaps we can only record ground motion within this passband. However, that's not true. As long as we know the instrument response, we can actually record things way beyond the passband. And here's an example that Adam Ringler has been working on using our new station at ANMO. And what he's doing here is he's filtering, this is east component data between, I think, 10 and 26 hours. And what you're seeing here are actually earth tides caused by lunar cycles. So this is the same kind of change in gravity or acceleration. They're driving the ocean tides on the planet. And what he's doing is he's comparing these acceleration signals seen on the STS-6 seismometer to a synthetic model, which is fairly well known. And we're matching these synthetic tides, which are, again, happening at about 12 to 24 hours period, to about 2%. So if you think about it, the corner instrument of the STS-6 is here at 360 seconds, and we're accurately able to resolve signals out here at 12 and 24 hours period. And the reason we're able to do that is the instrument response is well defined, so we can correct for that to bring it back up and get accurate amplitudes of these tidal signals. In order to do this, though, you have to have a very well-installed seismic instrument that has both low self-noise and is not being contaminated by thermal, magnetic, and other signatures, which I'll talk about. So I want to discuss this figure a little bit, which is this kind of a background figure showing what we'd like the global seismic network to look like in terms of operating range. So I have ground acceleration on the y-axis here on a logarithmic scale, and period in seconds also on a logarithmic scale on the x-axis. So what we consider the dynamic range of a seismometer is the signals that it can actually record. And it's bounded on the bottom by the self-noise of the seismic instrument. So instruments generate some type of thermal and electronic noise within the instrument itself. And if you have a signal that occurs below the self-noise of the instrument, you're unable to see it. On the top, we're bounded by the clip levels of the instrument. That's the maximum signal the instrument is able to output. And between these two, we call this dynamic range. So this dynamic range is frequency dependent. So if you consider this whole frequency amplitude space over which a seismic instrument can record signals, some people refer to that as the operating range of your seismic instrument. So here I show kind of the frequency response of a magnitude 9.5 earthquake at 30 degrees. So it looks something like this. And if you think about the seismic systems that we had recording in the 60s and 70s, shown here in these gray boxes, they'd fail to record this event. And the reason they'd fail is this is the clip level of the instruments, and we're having ground motion up here, so it's above what the instruments can record. Similarly, if you had a magnitude 5 earthquake at 30 degrees, this system would also fail to record that because it's below the self-noise levels of the system. Also plotted on here, I'm showing the low Earth noise model. This is what we think the quietest the planet can be in terms of ambient seismic background noise. And I'm going to say that we actually don't know the quietest that the Earth can be in terms of ambient seismic background noise in this region right here, because we're limited by the self-noise of the seismic instruments. The GSN design goals say that we want to be down here, but we're not quite there yet. And I'll talk a little bit about perhaps what we can do to try to improve upon this. By the way, that Earth tide signal I was showing is right there, and you can see it's above the low noise model, which is why we are able to record this, above the self-noise of the instrument here. Okay, so let's do a quick example of this. I've been thinking about Raspberry Shake seismometers a lot lately, and this right here is a Raspberry Shake. It's a relatively low-cost sensor. This costs about between $500 to $1,000, depending on how you option it. And it consists of a vertical component geophone here, a 3-component MEMS accelerometer, and an integrated digitizer that uses SeedLink. This uses NTP timing off of the internet. So it's kind of an all-in-one unit. You just plug it into an Ethernet connection, give it a power, and you can pretty much easily get off and running getting mini seed data in near real time. So this has been proposed, since they're so low cost, for densification of seismic networks, as well as for earthquake early warning applications. And I'm kind of testing this in relation to a USGS aftershock deployment, which consists of an RT130 digitizer, a Trillium compact seismometer, and an epicenter accelerometer. So both of these things contain a weak motion sensor and a strong motion accelerometer and a 24-bit digitizer. The difference is that this is about 20 times more expensive than this, so kind of keep that in mind. So if we look at this operating range of a Trillium compact, or of a Raspberry Shake, there's kind of two operating ranges here. There's the self-noise level down here of the geophone. There's a clip level up here of the geophone. There's the self-noise level of the accelerometer. And then there's the clip level of the accelerometer. And then you have these different regions where if you're below this level of power, so on the, again on the x-axis, I'm showing frequency in hertz. In the last GSN diagram, I was showing a period in seconds, but same thing, they're just inverse relations. And then I'm showing amplitude here on the y-axis. So let's kind of see how different earthquakes would be recorded by this instrument. So let's say you're in Oklahoma and you see a magnitude 3.5 at 100 kilometers. This is going to be well recorded on the geophone. It's above the self-noise level of the geophone. It's below the clip level, but it's pretty much below the self-noise level of the accelerometer. So you're not going to see this event on the accelerometer, but you'll probably record it very well on the geophone. Let's say you're in California and a magnitude 6.5 happens on the San Andreas and you're at 10 kilometers. You're not going to record this on the geophone because you're going to clip the geophone here, but you will see it on the accelerometer. And this is kind of one of these reasons why these instruments are being proposed, is because you could get peak ground acceleration of large events very close to the event. But how can self-noise levels be a limitation? What I'm showing here are power spectral densities with frequency on the x-axis and hertz, amplitude again on the y-axis for co-located instruments in our seismic vault at ASL. So I've co-located a Raspberry Shake, a Trillium Compact, and an STS-2 seismometer, which is kind of a higher quality seismometer, we'll say, than a Trillium Compact. And so I'm recording PSDs of these different instruments here. And what you can see here is that the Raspberry Shakes have a higher level PSD than the Trillium Compact and the STS-2. And why that is, I've also plotted self-noise of the Trillium Compact, here is this curve, and self-noise of the Raspberry Shake, here is this curve. And the reason why the PSDs are higher is because here you're not recording any actual ground motion on the Raspberry Shake. You're just recording self-noise of the instrument in this region. Here's the secondary microseism band right here. The Raspberry Shake can kind of barely see it, but you see that it's still a little bit higher than the STS-2 and the Trillium Compact. And what's going on there is that the Raspberry Shake is seeing both its self-noise, its a contribution from the self-noise of the instrument, and actual ground motion, so you have an artificially too high signal here. And since the self-noise levels of the Trillium Compact and the STS-2 are so much lower, they record almost identical power spectral densities throughout this entire range. Down here, I've plotted the same thing except for the accelerometer. So again, here's what we think true ground motion in the vault is looking like as a function of frequency. And you can see that the accelerometer isn't really recording any of this. It's just entirely instrument noise that you're getting. So how do we measure this? So if we're interested in getting the self-noise of the systems, how do we do this? To get the digitizer self-noise, we do a terminated input test where we take some resistors that basically mimic a seismometer with no noise. And we just record for a few hours and take the power spectral density of what's recorded with basically no input going to the digitizer. And that's what this looks like. And as you can see here, at longer periods, we're really not limited by the digitizer. The digitizer self-noise is a lot lower than the self-noise of most broadband seismic instruments that you're attaching to it. So this is a self-noise model here of a Nanometrics Trillium 120. So how do we do this for seismic sensors? We use something called 3-channel correlation analysis. It's very nicely written up in Sleeman et al. 2006 in BSSA. And basically the way the method works is it assumes that true ground motion on 3 co-located sensors will appear as a coherent signal in all channels. And any signal that's incoherent amongst all the sensors, any signal that looks completely different, it attributes to the self-noise of the sensor. So here's an example of 3 co-located sensors. Here's the power spectral density of the sensors. And down here, I'm showing the self-noise of these. This is the incoherent noise of the sensors. And you can see on these are kind of a Trillium Compact type sensor. At about 30 seconds period, all the signal you're recording on these is essentially self-noise of the sensor. So how do we actually do this test? We install 3 sensors next to each other. Here are the Raspberry Shakes in a fairly thermally stable environment. I'll show kind of why that's important in a few slides. And then we record background noise for several hours. And we actually have a software package to do this. It's available on Github. It's completely open source, written in Java. And we recently had a paper out on this in SRL. And it's a pretty intuitive software package. You just load in the data from the 3 sensors. So here I'm loading the north component of 3 of these Trillium Compact-esque sensors. And you load in the response, and it does the Sleeman analysis, and here's the power spectral densities, and here's the self-noise of the sensors. You might notice this little bump right here that we have in the self-noise, and that's kind of arising because these sensors are not perfectly aligned. So we're looking at a north component. Everything's not perfectly aligned towards north. So you get some incoherent secondary microseism signals here that the algorithm is attributing to self-noise. This can kind of be mitigated by doing a 3-component analysis where you rotate everything into a common orientation, but that's maybe beyond the talk a bit. Okay, so with self-noise kind of taken care of, I'd like to talk a little bit about non-seismic noise sources, and we're going to be talking about thermal variability. And Claire Duty, our own IRIS intern in 2017, did some work on this. We'll talk about magnetic fields, and we'll talk about pressure. And this is a photo I took back as a grad student when I was up on Cotopaxi volcano at about 16,000 feet, and I had a water bottle, and we went back down to I think about 8,000 feet, and it's pretty impressive just to see how the water bottle, crushed under the changing pressure. So thermal variability, what I'm showing here are 3 co-located sensors in a vault in Tucson. So this top trace is showing an STS2, or STS1 rather, in water bricks. And if you're wondering what a water brick is, it's kind of these Lego shaped containers full of water. And what a water brick does is it really increases the thermal capacity around the seismometer, so that changes in ambient temperature don't reach the seismometer. It attenuates changes in ambient temperature. We have an STS2.5 in a foam box, and we have a post-hole STS6 that's about 1.4 meters below the surface of the vault. And the data I'm showing is acceleration output that's been low-pass filtered at 1,000 seconds. So that's the blue trace, is this low-pass filtered acceleration data. The red trace is showing temperature data, relative temperature data. So we've just removed the mean. And this is all showing the same time period. So you can see that in the foam box, we have, thermal variations over this course of 50 days in the vault of about peak to peak 1 degree centigrade. But by putting the sensor in water breaks, we've essentially halved this thermal variability that we see in the vault. We've taken a lot of it out. The other thing that I want you to notice is that the output of the sensor is directly related to changes in temperature here. So right here we have a Pearson's correlation coefficient of 0.89. So it's showing that this signal here on the seismometer is probably definitely driven by changes in temperature. Same thing on the STS 2.5 here. And this one's a little bit tricky because the temperature sensor is actually sitting on the top of the post hole, so the thermal variations seen by the sensor are probably much less than what the temperature probe is seeing here, which may partially explain this low correlation coefficient on this instrument. So it turns out that thermal variability can also influence the self-noise instrument, or self-noise measurements I was talking about earlier. That's why it's pretty important to conduct your self-noise test in a thermally stable environment. So looking at the bottom panel here, these are 3 different types of sensors. This is an STS2.5. This is a Trillium-120, and this is a Trillium Compact. And what we're doing is we're looking at self-noise levels as a function of thermal variability, where cooler colors are showing that it's a very thermal stable environment, and the red colors are a very thermally unstable environment. And the way Claire did this is she wrapped the boxes around the sensors in heat tape and was basically driving the thermal variations herself. And what you can see here, particularly on the Trillium-120, is that if you have higher thermal variations, the self-noise of the instrument increases drastically. So this is just kind of showing why it's important, especially when doing self-noise tests, actually why it's important in general to keep an instrument thermally stable. You're artificially raising self-noise levels of the instrument, which can't be removed easily if the sensor is seeing thermal variability. So how do you mitigate this? We kind of talked about water bricks, which is increasing the thermal capacity of the instrument. Another way is to just kind of get away from thermal variations. And what I'm showing here is how deep you'd have to go below the surface for a seismometer to essentially not see changes in temperature for different materials. So what we're doing here is we're assuming a temperature pulse on the surface. So this is maybe the diurnal temperature change you'd see. Here's depth in meters, and this curve right here is showing below this curve, you're deep enough that you're not seeing thermal variations. And what we're doing is we're modeling the thermal diffusivity of these different materials. So if you're in sandy soil and you have, maybe you're in Albuquerque and you see 20 degrees of temperature variation on the surface and you don't want that to impact your seismic observations, you have to go down to something like 80 meters depth or so to make sure your seismometer is not seeing thermal signals. Granite has a much higher thermal diffusivity, so the same 20-degree diurnal temperature variations, you'd only have to go to down maybe 35 to 40 meters depth to take out these temperature signals. Okay, so Besides thermal effects, seismometers also see magnetic fields. And the example I'm showing here comes from College Station, Alaska, which is up by Fairbanks. And what I'm showing here are the primary and secondary vertical component ground velocity bandpass between 100 and 1,000 seconds period. And you kind of get, these nice things that kind of maybe look like surface waves here on both sensors. But if you look at the magnetometer data, you see that you have the same signal. So all these things we're seeing on the seismometer here aren't actually surface waves like they might appear on first inspection. They're actually just the seismometer responding to changes in magnetic flux. So why are seismometers sensitive to changes in the magnetic field? Well, when manufacturers make seismometers, they're trying to make the springs in the seismometers thermally stable. So the expansion coefficient of the springs is very minimal, so that the springs don't expand to contract with changes in temperature. And the alloys they use to have this thermal property almost necessitates they use ferromagnetic alloys. So what that means is that the springs often have some type of small remnant magnetism imprinted in them, where the domains within the actual springs are aligned in some preferential direction. So then when they have a magnetic moment, so when you see changes in the magnetic field, you generate a proportional apparent acceleration on the seismometer masses to the magnetic field. So how do we measure this in the lab? How do we measure how sensitive an instrument is to magnetic fields? We have a Helmholtz coil here, which we inject a current into to produce very large magnetic fields within the coil. We have a magnetometer here, which measures the magnetic fields, and we have our instrument under test. So we record the magnetic flux within the coil. So this is the magnetic field in Tesla within the coil. We record the seismometer output, and you can see here that this particular instrument, I'm showing an example of a Geralt CMG3T here, is sensitive to changes in magnetic fields. And essentially, all seismometers are. And the amount of how sensitive a seismometer is to magnetic fields has to do with if the manufacturer has provided some shielding, which we'll discuss in the next slide, as well as the materials used in construction of the seismometer. So how do you get rid of this noise source? Kind of the most common thing, which is actually rarely used, is to use something called a mu metal shield. And so this is an SGS2 seismometer. And here's an example of a mu metal shield, which kind of looks like a trash can, but it's a very expensive trash can. I think it's about $3,000 or so. So that's why they're not used often, especially in temporary deployments. And how the mu metal works is it provides a path of least resistance for the magnetic field here. So I almost kind of think of the mu metal shield as like the equivalent of a Faraday cage, where you kind of have a very highly conductive material that kind of guides the current or here magnetic field lines around the sensor, so that the sensor here is shielded from seeing these variations in magnetic field. And this is shown to be effective in reducing the sensitivity of seismometers to magnetic fields by a factor of 20 to 40. Unfortunately, as I mentioned, they're very expensive, and especially for temporary deployments, they're rarely used. So besides magnetic fields, seismometers also are directly sensitive to pressure. And I'm going to illustrate this with this little cartoon here, where I've drawn a seismometer just as a mass on a spring. You have some ambient air pressure, which acts as a downward force on the mass. And if I increase the air pressure here, the force on the mass becomes larger and the mass moves down. I can kind of toggle back between these two things. So you're getting a direct force on the mass, which is a noise source. Also, if you kind of go back to your high school chemistry and think about PV equals nRT, if you cause an increase in pressure, you're also causing an increase in temperature. And as we just discussed earlier, changes in temperature the seismometer is sensitive to. And then finally, the casing around the seismometer may deform in response to these changes in pressure, kind of almost similar to that plastic bottle example I showed, although not as extreme. And the seismometer might see these changes in stress as the casing it's in is deformed, or there might be pinging and popping as the casing is deformed in response to these changing pressure. So what do we do to mitigate that? Well, to mitigate the effect of the direct pressure response on the mass, kind of floating mass, and the thermal change, we try to hermetically seal the seismometer. And this is an example where we've actually just taken a stainless steel cooking pot with a rubber gasket on the bottom and bolted the cooking pot to a thick gabbro base plate. And the thick gabbro base plate is just a very stiff, rigid material that we don't expect to deform very much under changes in pressure. And this kind of setup has been shown to reduce vertical component signals attributed to pressure changes by above 40 dB. So besides direct changes in pressure, there's also kind of this indirect pressure noise in the form of tilt. So as pressure systems pass over the surface of the Earth, they're exerting a force on the Earth's surface. So you can think of the high pressure system comes over a region, it's causing a downward force on the Earth, which causes a small amount of subsidence in that area. And then the ground physically tilts in response to this subsidence. So what I'm showing here is something our Pathways intern Alexis Alejandro is working on. And this is an example from our station at Cathedral Caves in Missouri. And what I'm plotting here is pressure in red. And in black, I'm showing acceleration. And down here, I'm showing the coherence between pressure and acceleration between 200 and 800 seconds period on these horizontal components. You can see that for this about 11-day period, the coherence is quite high between pressure and horizontal acceleration at long periods, showing that this signal is being almost entirely driven by pressure-generated tilt at this particular site. So why are seismometers so sensitive to tilt? If you think of a seismometer sitting here perfectly level, our horizontal components are measuring velocity in this direction, and gravity is acting in this direction. So just sitting perfectly level, you don't see any component of gravity on the x component. The vertical component of the seismometer is seeing g exactly because it's acting in this direction. And this acceleration due to gravity is being balanced out by the suspension system of the seismometer. But if we start to tilt it at a small angle of theta, the y-axis of the seismometer sees gravity as g cosine theta, and the x-axis sees this gravitational acceleration as g sine theta. And I actually have to think about this in the reference frame of the seismometer to get these trigonomic relations to work out correctly. But if you assume a small angle approximation here, so we're talking, maybe microradians of tilt, essentially the vertical component doesn't see this small change, this g cosine theta acceleration, whereas the horizontal components actually observe an apparent very large acceleration. So basically tilting the instrument like this looks like a very strong horizontal acceleration. So, okay, is it possible for us to remove this signal? And this is some of the work by Max Rode, who is an Irish intern at ASL here in 2016. And Max set up an experiment in our underground West Vault where he took a bunch of STS-2s, 8 of them, and set them up in a kind of small aperture array. So this is 6 meters right here, so the farthest separation distance between instruments is maybe 8 meters or so. And he's going to look at how coherent signals are across these instruments. So how similar are very long period signals on these different seismometers. Actually, not even very long period. We're only really talking here about 30 to 50 seconds period. So what this diagram is showing is the gamma squared coherence, basically a measure of how similar are these signals between two sensors over a 5 to 7 hour visually quiet period. So this is a symmetric matrix. So here, you're just looking at the coherence of the sensor with itself, so it's all as one. But here, for example, you're looking at the coherence between sensors 1 and 2. And you can see that the coherence for all of these are quite high. So what this is saying is that at periods of 30 to 50 seconds, the vertical components of seismometers in this vault are all essentially seeing the same thing, and the world is pretty good. If you look at the horizontal components, completely different story here. A lot of these coherence numbers drop drastically. And so what this is saying is that where you have very low coherence, these two sensors, which are only situated maybe up to 8 meters apart, are seeing drastically different signals. And if you think about the wavelength of these signals, if you think they're a surface wave or something, maybe like a 30-second surface wave traveling at 3 kilometers per second, has a wavelength of about 90 kilometers. So if this is an actually elastically propagating seismic wave, we'd expect these signals to be practically identical on these stations separated by just a few meters. But they're not. They're all over the place. So let's kind of look at a few examples here. Looking at stations 1 and 8 here, you can see that these two are highly correlated with each other, so they see very similar things, but all the other sensors in the vault see something completely different. We have very low coherence with all the other sensors in the vault. And perhaps this is being driven by something like a wall effect, where this wall is actually physically moving back and forth in response to pressure, and maybe these two sensors are the only ones seeing it. Stations 7 and 6 see pretty high coherence. In fact, they're the highest coherence pair in this group, which you maybe anticipate since they're the closest together. But 6 and 3 also show the second highest coherence, and they're not the closest together. And 2 and 4 actually have the lowest coherence outside of 1 and 8, and they're right next to each other. So I guess, kind of in summary, this is a very complicated effect that's highly incoherent on very short spatial distances. And the kind of impact of this is that it's very difficult to remove this signal from seismic records. And kind of the other impact, if you're thinking about self-noise estimates, is that since you have an incoherent signal between these two sensors located right next to each other, it could artificially raise self-noise estimates on the horizontal components of sensors, because you're getting an incoherent signal, and the Sleeman analysis is going to assume that this is self-noise of the instrument when it's actually likely just a tilt signal. The only way we know to mitigate this effect right now, I think, is to install a sensor at great depth. Sorrell's 1971, I think, said if you get below 300 meters or so, this effect should mostly go away. But there are some actual applications to using these tilt signals. I know the volcanology community uses them occasionally to look at deformation on volcanoes, so they use it essentially as a tilt meter. This is kind of an interesting application in the California desert, where they're looking at the passage of dust devils, little vortexes, using tilt on the seismometers. So there's a co-located Trillium compact. There's a wind speed anemometer. There's a pressure sensor. And so here you get these kind of drops in pressure, which are suggesting that you have a vortex passing. At the same time, you see an infrasound signal. And then you get this tilt signal here, which looks like an east-west and north-south acceleration. And here they're actually using the signature of this tilt to try to get a trajectory of the vortex and kind of get some of the characteristics of the vortex, like how large it was, what the pressure drop in the center of the cyclone was. And kind of the idea of the application of this is that currently we're sending a seismometer to Mars on the InSight mission, and perhaps this could be used to identify, similar vortices on the Martian surface. I ran an experiment with Rick Astor and others at Colorado State University in the Rocky Mountains that Andy alluded to, where I installed 3 L28 geophones here within about a meter of the Cachalaputa River. So this is a snowmelt-fed river coming out of the Rockies. And I saw some very interesting signals that I wasn't anticipating on these instruments. So what I'm showing here is a power spectral density probability density function, which is kind of a mouthful for these instruments. So I'll kind of step through what this is slowly, hopefully, because I'm going to be showing a few more of these when I talk about seismic background noise. So the y-axis here is showing you amplitude again, kind of like those other plots I've shown. The x-axis is again showing frequency in hertz. And here the color scale of the histogram. So what I've done is I've plotted up thousands of power spectral densities on top of each other here, and the colors are showing you how often these different power spectral densities kind of show up in these different bins. So if it's a darker color, that's showing you that the seismic background noise is often in this region. So like here, a lot of the time it's sitting here. And if it's a lighter color, it shows very rarely. So very rarely do we have these kind of extremal high energy events. And then if it's dark blue, that means the seismic energy is never in this level. Okay, so plotted on top of this, I'm showing median power spectral densities for different levels of discharge in the river. So the thick black line on the bottom is 1 to 2 meters per second, and the thin line on the top is 10 to 16 meters cubed per second. So this is a peak snowmelt runoff, and this is kind of a background conditions. There's not much water coming down through the river. And what you can see in general is that if you have more level or higher levels of water coming down through the system, you get more seismic energy, particularly at these periods of about 0.2 to 0.3 hertz or so. So this is about 5 seconds to about a half a second period. And we're going to use this signal actually, which we found is a tilt signal because it's so high energy and it was so different between those sensors that were just located 15 meters apart, using that same argument that we used for Max's observations, that these are tilt signals being generated by the river. And this is where self-noise almost bit me here, is that what you're seeing here is just self-noise of the L28 geophone. You can't make any observations, even of these tilt signals at low discharge rates, because you're limited completely by the self-noise of the geophone. So then you're actually only able to record energy in this frequency band at the highest levels of discharge in the river. So this is just kind of an example of why self-noise of the instruments needs to be taken into account and how it can impact your ability to make observations. So I did a simple kind of regression during a calibration period during a rainstorm here. So during this rainstorm, discharge spiked drastically. So on the y-axis now I'm showing discharge in meters cubed per second, and time is on the x-axis. So here's this rainstorm event, which I used to create a relationship between this tilt signal and discharge. And then I use that to model a synthetic discharge, a synthetic hydrograph, if you will, during the rest of the experiment. And it matches a lot of these features quite well, including these diurnal variations in discharge. So this is caused by, during the day, there's more snow melt, so discharge spikes a little bit, and then at night, there's no snow melting, so discharge drops a little bit. Here's kind of, peak snow melt, and then kind of falling off here as the snow gets depleted in the mountains. And then down here, we had a late season dam release, and the synthetic hydrograph matches that quite well. So it seems that, in the near field at least, we are able to use these tilt signals to invert for things such as discharge in rivers. Okay, so that kind of leads us into this third topic, which I'll go through quickly, is seismic background noise. This is the actual seismic signals now that we are recording on sensors, and it's kind of given the term noise, although I think now it's some people's signal, because it can interfere with our ability to observe earthquakes. So here's showing the exact same figure. It's a power spectral density probability density function, where again the colors are showing you how likely you are to be in these different noise regimes. And so red again is very likely to, oftentimes we're sitting down here. We're looking at South Pole Station in Antarctica here, by the way, and then we're looking at about 90,000 individual 1-hour PSD estimates. So often it's very quiet at a short period, but sometimes it gets very noisy. So what's going on here, I used to think that, kind of the dominant drivers of short period energy are cultural noise and wind. It seems that cultural noise in most stations is actually the dominant driver of short period or high frequency energy. So what I'm showing here is a time series of power in this band. So you can see that every summer, energy at short periods jumps drastically. And what's going on here is that this is when they're grooming the runways down in Antarctica. So they're having large tractors and things moving at South Pole Station. There's a lot of activity at the station, and so anthropogenic noise here jumps up 20 dB. And then in the winter, so winters like July in Antarctica, it's very, very quiet. kind of recently, we've kind of seen that maybe rivers are also generating high frequency noise. So if you're putting a sensor in close proximity to a river, you'll also record high frequency energy. And also surf, so like next to oceans, breaking waves also appear to generate very high frequency energy. Moving on to longer periods, here's the secondary microseism, which is caused by ocean waves. Here's the primary microseism, which is the direct coupling of ocean waves with the continental shelf. And then out here, we kind of think of this as Earth's hum usually, which is the nonlinear interaction of ocean waves. So these are kind of all ocean wave generated background noise in the absence of these other drivers that I've been talking about. So moving on quickly, this is an example of a spectrogram here at this station in the Dominican Republic as a hurricane passes by the station. This is a high frequency noise observed on the station, and it's probably anthropogenic noise because you can see it has a very strong diurnal cycle. So we think this is pump noise from the dam. In spectrogram form, this is what an earthquake looks like. It's very brief in time, and it's putting energy out across a variety of periods here. And so this is typical kind of ocean background noise recorded this station. And then here's a hurricane coming through, and you see this very large noise source. This is just kind of an example of a station recording a multitude of different types of background noise. So this is a station in the Keweenaw Peninsula of Michigan. And you can see this, this is a secondary microseism right here. It has a very strong seasonal variability in the Northern Hemisphere. So the biggest storms in the ocean in the Northern Hemisphere happen in the middle of the winter. So that's why we have a peak here and a trough in the summer. But there's also kind of this higher frequency or shorter period signal happening between 2 to maybe half a second to 2 seconds that also has a seasonal characteristic to it. Except there's these time periods here where this kind of shorter period signal is missing. So what's going on there is here's our station, and during that time period I showed where that signal is missing, the Great Lakes froze over, and I think they've reached their highest concentration of lake ice since the 1970s in 2014. So this is a signal that's being generated by the lakes. It's probably like a small scale version of the microseisms that we see in the ocean. I was interested in seeing how prevalent this signal was. And so what I did is I looked at power spectral densities during that 2014 polar vortex over 3 weeks in early March. So that's this power spectral density right here. I used the exact same 3 weeks for all non-frozen years, so just this kind of the average power spectral density in early March for when the lakes aren't frozen. And so this kind of void right here is maybe suggesting the energy that's being put into the solid Earth by the Great Lakes, by wave action in the Great Lakes. And kind of taking the difference of these for several stations, it seems like this lake microseism signal happens between maybe 0.65 to 3 seconds period, and it can impact ambient noise observations around the Great Lakes by up to 17 dB or so. And then I just made a contour map of all these TA stations that were fortuitously in the area at the time, and you can see that the largest signal from these lake-generated microseisms are up here in the Upper Peninsula of Michigan, and they kind of fade out. But the 3 dB level, which as a reminder is about twice as much power, you can see this signal through a majority of the Midwest. So I think I'm kind of running a bit over time here, so I'll just quickly go through the takeaways. I just want that accurate measurements of ground motion can only be attained if the ground motion is above the self-noise of the sensor and below the clip levels of the sensor. So if your signal is not within the dynamic range of the sensor, you're not going to record it. Non-seismic noise sources and tilt can also limit our ability to accurately determine ground motion. And finally, ambient seismic noise sources are being increasingly utilized by the seismic community as a tool for understanding Earth surface processes. So with that, I will take any questions if there are any.
Thanks, Rob. That was great. So we have, I would encourage everybody, get your questions in, type those in right now. I have one already queued up from earlier in the talk. Denise Templeton was curious what was causing the magnetic flux that you were seeing at the College Station in Alaska.
Well, these could be magnetic storms, right? The same thing that causes the aurora borealis. So it's just changes in the magnetic field at this station. So it's most prevalent at higher latitudes just because the magnetic field is stronger at higher latitudes because you're closer to the poles.
Great, thanks. Okay, so we have a couple more questions that have come in. I'll just start going through these in order. So there's one from Ross Caton, and he asks, what is the best way to remove the effect of magnetic fields on noise-dominated seismograms?
Well, either you co-locate a magnetometer with your seismometer and you know the sensitivity of the seismometer to magnetic fields, and so, you know, that's expensive and difficult, or you take steps to provide adequate shielding so that the seismometer does not see magnetic fields, and that's also expensive. So I guess in the sense of temporary deployments, I don't know an easy way to answer that. I think it's very difficult if you don't have co-located measurements of the magnetic flux and you don't have a shielded instrument to remove the signal once it's in your seismic records. You might be able, so we have a magnetometer at College Station, Alaska. So if you're, perhaps working on the TA Alaska data set or a flex array up there, you might be able to use the magnetometer data to at least recognize that there is a magnetic storm happening, there's very large fluxes, and kind of anticipate that you might see this on your instruments. And I think in the GSN, we run 4 or 5 magnetometers across the globe at high latitude regions that you could maybe use to just to observe the signal and see if it's occurring and perhaps make a rudimentary correction in the data.
Thanks, Rob. Next question's from Scott DeWolf, and Scott asked, did you say whether you evacuated the stainless steel pressure container? If not, why not?
Yes, we usually do evacuate the stainless steel pressure container, and the reason for that is it reduces thermal noise. So we want to get as much, I think of it as we want to get as many air molecules out of there as possible so that they're not kind of knocking into the masses of the seismometer and causing noise. And also, when you evacuate the air, you kind of, pull out any moisture that might be in there. And of course, moisture can cause corrosion of components within the seismometer, which can create a whole nother set of problems.
All right. Next question is from Brian Shiro. Brian asks if you have used water bricks in a field surface fault scenario to reduce thermal variations when digging deep isn't possible. And if so, have those bricks held up to the elements like UV rays?
Ooh. I know we've used them in a few seismic vaults such as Tucson, and we've had ours out in the Albuquerque sun for, maybe a year, and we haven't had any leaks yet. I don't know that we've done any deployments where we've had water bricks exposed to the sun for long time periods and how they, if they would degrade and start leaking over time. I'm not sure.
All right, next question's from Bob Busby, and Bob asks, since you showed the high coherence between pressure and tilt, has anyone tried to remove the pressure signal from the seismic signal?
Yes, lots of people have tried that to varying levels of success on different stations. So something like cathedral caves, where you have a very large tilt signal, it might be possible to empirically derive relationships between pressure and tilt to remove that from the seismic records. But it's not completely clear what you're actually doing when you do this, and it doesn't seem to be applicable to all seismic stations. So it's not, yes, lots of people have tried this. It's not clear if it's how widely applicable it is and exactly what you're correcting for, I think.
All right, next question's from Stephen Mosher, and Stephen asks, how might one go about addressing tilt effects in stations that are not already buried? How much can the tilt increase the floor of the self noise?
Well, I think that fundamentally tilt does not increase self-noise levels of the sensor. It increases the apparent self-noise levels of the sensor because it's an incoherent signal. So I just want to make sure there's no confusion on that. I think that's at least that's how I see it. How can you mitigate tilt signals on instruments installed on the surface? There's been some work by Emily Wolin and others that if you put the instrument on a more rigid surface, you can mitigate tilt. So if you put in like a soft sandy soil, these atmospheric driven tilt signals are likely larger than if you place the instrument on granite where possible. I know that sometimes when we make site selections, we don't have the luxury of always putting our instruments on, you know, the most stable platform. There's also been a little bit of suggestion, which I'm not sure if this has been definitively proven yet, but it seems like perhaps direct buried instruments might have a little bit less pressure tilt susceptibility than vault instruments. And I think this is kind of still an area of active research.
All right, thanks, Rob. So next question's from Adam Klinger, and Adam asks if borehole sensors are less affected by magnetic field flux.
That's a very good question. So in that first Tidal slide, I actually was showing us testing the magnetic susceptibility of a sensor in a TA Alaska style casing. And what we observed there is that the casing actually seemed to increase the magnetic susceptibility of the sensor. So we had our magnetometer in there with the casing of the instrument. So we're still just getting the response of the instrument to a magnetic field inside the casing. And it almost seems like the sensor becomes more sensitive to magnetic fields within the casing. And I don't think we exactly understand why that is, if the magnetic flux lines are maybe focused in the casing. But it seems like some of these stainless steel casings could actually enhance a sensor's sensitivity to magnetic fields. But that, again, is an active area of research, I'd say.
All right. Question is from Edgar Montoya, and he asks, what are the main recommendations you can make to avoid noise?
I think that, you know, it kind of depends on the type of deployment and your budget. I think the thermal stability by burying the instrument is a big one. Trying to reduce the wind profile of the instrument is a big one, to try to keep any large structures or the top of the vault from sticking out, or it could couple with the wind and cause tilting of the sensor itself. I think magnetic shielding for most applications is not necessary, especially at lower latitudes. This is really predominantly an effect we see at higher latitudes. But yeah, I'd say trying to thermally insulate the instrument as much as you can by going as deep as, you know, reasonably possible, and putting the sensor away from known noise sources, you know, such as railroad tracks and trees and other objects that could likely generate signals that you don't want to record.
All right, next question is from Brian Shiro, and Brian asks, are silicon audio sensors less sensitive to magnetic noise since they don't have springs?
Ooh, that's a good question. We did not run a silicon audio sensor through our Helmholtz coil yet, I don't think. At least I don't know the results of that off the top of my head. I'm not sure.
There's a comment from Brad Advinson, who's actually works for Silicon Audio, and he notes that they actually do have springs in those sensors. So that follows up on that. So question from Johan Samin asks, what is the best way to mitigate cultural noise caused by machinery such as marble or granite cutting machines?
Get as far away from the marble and granite machines as possible is the best answer I can give. Since the cultural noise is typically higher frequency, that means it attenuates more rapidly with distance than longer period noise. So I think distance is your best friend in these scenarios. Yeah, that's in general. I'd just say, yeah, get further away from these noise sources.
All right, and another follow-up from Brad. He just adds that the springs in the silicon audio sensors are copper, so they are not inherently magnetic. Follow-up, another question is from Suzanne Vanderlee, who asks, you explain that enclosing a sensor in vacuum air, sand, or granite determines to what extent seismic recordings are affected by temperature. Do those enclosures and or the temperatures they achieve and or other aspects of their constitution determine to what extent seismic recordings are affected by pressure and tilt?
That's one I'm going to need to think about a little bit. If that one could be sent to me in an email, I'd be happy to discuss that one with my colleagues and get back to Susan.
All right, no worries. And then, so the last question I have queued up is from Simon Staller, and he asks, did you have any insight into the shielding efforts, wind or pressure, etc., done for the InSight seismometer on Mars, and do you have an opinion on it?
I don't. I'm not very familiar with what type of shielding they're using on that particular sensor, so I don't have an opinion on it. I wish I knew more about how they're shielding that particular sensor, but I don't know hardly anything.
All right, another question's come in from Sarah Oliva, and she asks, can the pressure differential that causes wind generate seismic noise, or is the noise primarily due to the tilt caused by nearby structures?
That's another really good question. Our IRIS intern from this past summer was kind of working on this type of thing, and I think it's both. So I think that's my sense anyway. This is kind of just my personal opinion. Is that yes, you can get when you have wind events, you have very local changes in pressure, which can drive direct tilt of the sensor. But you can also have the wind coupling with buildings, which can also drive a tilt of the sensor. And I think you can probably also, have the building generate high frequency actual seismic signals in the ground as well. But yes, it certainly generates, wind certainly generates a plethora of seismic noise signals through different mechanisms, either through generation of a tilt signal, generation of a pressure effect, or actually causing a vibration of a structure or a flag or a rod or something, which will put high frequency energy into the ground. That's what I think right now.
I think there's some examples from the TA where there were wind turbines in proximity to the stations where you could start to see the signal generated by the actual structure. So yeah, I think there's some pretty clear examples out there from recent deployments.
Oh, and wind turbines are a huge noise source that can be seen, 20 to 30 or more kilometers away from the station. Omar Marcio just had a paper come out, I think, in SRL on detection of wind turbine noise, and this is actually the wind turbine moving back and forth in the wind and generating a high frequency seismic signal. So it's actually an elastically propagating wave, not just a tilt signal.
Exactly. So, yep. Well, great. Well, Rob, that's all the questions we have. There were a couple comments from Mouse Royce and Heather Deshawn at their institutions that said, great talk. There was a nice audience of people that were in various seminar rooms watching. So thank you so much. I would encourage anybody, if they have follow-up questions with Rob, sounds like you're happy to receive those over email. And,
oh, yeah, absolutely.
And I'll finish recording this in a moment, put it up on YouTube, and then it'll be available through the IRIS Playlist B on our YouTube channel as all of our webinars, over 100 of them at this point. So thank you, everybody, for attending. Rob, thank you so much. That was great. And everybody have a great rest of your afternoon.